Hello everyone, I'm Bo. I'm currently a program manager in data science space. In part 1 of this video, I cover the big buzzwords. This includes AI, machine learning, deep learning, NLP, and ASR. I also went over different types of algorithms and why they are useful. In this video, I'm going to deep dive into the technical side and walk you through the modeling process, as well as the metrics that we use to evaluate how good our models are. If you want to jump to a particular topic, I have included a timestamp below to make that easier. Now, let's jump into it. For the modeling process, I want to break into 2 phases. The first phase is when we develop the model itself. In this period, usually only the data analyst, data engineers, and data scientists are involved to build the model in a notebook. It's often referred to as either the proof of concept or minimal viable product phase, the MVP phase. Once we have proven the value, we will productionize it. This is when we have data engineers and ML engineers heavily involved in building the pipeline and deploying our model so it can run automatically and continuously. Let's first look at the process during the model development. When you first start a project, your boss has this amazing idea. As a PM, it then becomes your responsibility to see the data scientists make this golden idea a reality. What do you do first? You are going to work with data scientists or analysts on the exploratory data analysis, so EDA. Don't worry too much about the terminology here. What's important to remember here is just know that what's going on with the data. Ask yourself and find the answer to the following questions, like which features are correlated? How is this trending? For example, if we have this cute cat outfit, what feature might impact it? Is it seasonality? Is this in any way related to the cute dog outfit? There are a lot of questions we could find answers to through this EDA before we go on to the modeling. We don't want to build a model only to realize that there is no relationship at all between the feature we're trying to predict. After EDA, we have a rough idea on what we are working on. We can then start data pre-processing and feature engineers to prepare for the modeling. Right now, a lot of companies are building feature stores because there are more and more machine learning models every day. People have realized that many models have been using similar features. So rather than reinventing the wheel every time, why not just build a feature store which is pre-processing the data? And why not just also, while you add it, complete the feature engineering part too? So especially if the feature tends to be shared between the different models. Regardless of if you build the feature yourself or you find the feature from the feature store, after this step, we are finally getting to do some modeling. You'll be surprised that the modeling step is actually usually the easiest and less time-consuming compared to the data preparing step. In most modeling cases, you just need to use the existing libraries or packages. Unless you are building a super complex neural network from scratch, you will likely only need to call some function and let the model just do its thing. You might need to adjust some parameters a bit to improve the performance, but you might need to spend a couple months of EDA and getting the data ready before you can do the modeling part. Alright, we are moving on to the productionization. Let's say you already have the model the data scientists built in their own notebook. You run in batch and it works. If you just need the modeling result periodically, you can just use a notebook to run it. For some use case, great, it went well and you are done. Job finished, golden idea complete, and you celebrate. However, if you need to actually run it continuously and automatically, this is where the ML Ops team come in. That is your machine learning and data engineers front. They will take the notebook, migrate to GitHub, configure the files, and set up the data pipeline to enable continuous training. The CI/CD here means that they will continuously integrate and continuously deploy. This is commonplace in the software engineering development process. The ML Ops team will also monitor the model performance and run the experimentation. Since ML Ops is just still novel ideas, that becoming popular in the last few years, there are still times where data scientists are doing those model productionization. If they do, they should get paid more. Just saying. So, is your company following a similar process? Do you have an ML ops team? Comment below and I would love to know. Alright, let's move on to the bread and butter for PMs. Matrix. So different models will have different metrics to evaluate performance. But I want to focus on the most common type of models, regression and classification. Rather than explaining different metrics and the equation used to derive those numbers, I'm going to focus on how to interpret those metrics. Because no one likes another college class. And you will close my video if I show any mathematical equations. So I will focus on explaining how to interpret those metrics. Is the number larger the better or the other way around? So you can sound like a quite intelligent person and know what you're talking about when data scientists show you the model performance. When it comes to regression model, we are predicting a value. So to evaluate if the model performs well or not depends on how close our predicted value is when compared to the actual sample value. Here are the top 3 metrics for model evaluation. All of these measure how well your model fits the testing dataset. The first one, R-square or adjusted R-square, is between 0 and 1. The higher the number, the better. So if your R-square is 1, that means your model is perfect fit to the data, which also means that your model is wrong because it's just impossible to have a perfect fit. The next 2 metrics, since those all have the arrow in it, as you might guess, generally the smaller number it is, the better the model performance is. Moving on to the classification. In classification problem, the model is evaluated based on if it can guess it right or wrong. It is a chihuahua or not. So the metrics that are used are if the answer were identified correctly or not. So here are the top metrics here, and all this definitely can be confusing, much like in the name, confusing metrics. I'm going to spare you and myself by not going over each matrix here. Just remember that the position, recall, F1 score, and accuracy are all just different ways to evaluate how accurate modeling results are. Usually, accuracy is super straightforward, but F1 score can be just as if not even more useful than accuracy, since F1 score takes into account the different ways or scenarios. Since we covered some basic metrics for model evaluation, another set of terminology that you will hear data scientists see all the time are bias versus variance, and underfitting versus overfitting. Both bias and variance signify errors. Bias stands for the error because assumptions in the learning algorithm are overly simplistic. This assumption can lead to the model underfitting the data, making it hard for the model to have high predictive accuracy. It also makes it tougher for you to generalize your knowledge from the training set to the testing set. Variance is also an error because too much complexity in the learning algorithm. It can be the reason why algorithm is highly sensitive to the high degrees of variation in the training data, and that sensitivity can lead to your model overfitting the training data. With variance, the model tries too hard to fit the training data, but when it gets to the testing data, it isn't very useful in predicting what's going on there. Basically, the model is just carrying too much noise from the training data to be of much use when it comes down to your testing data. In general, too much bias leads to underfitting, too much variance leads to overfitting. And the question I usually get is, how much do you actually need to know to become a machine learning PM? I have taken many machine learning classes and have seen how hyper-technical it can be for PMs. Realistically, in a real-world, day-to-day PM position, you don't really need to know all the details about the model, and you are not expected to review the code itself. But you should and will, however, need to understand the process and key concept so you can navigate the decision on the technical approach and plan the project. For that reason, this is why I wanted to make those videos to go over the concept that I find myself very useful to learn in my daily job as a PM in data science. I hope this helped clear up some of the most common questions that you have regarding to machine learning. And thank you so much for sticking to the end. This video takes a ton of time for me to write and produce, so it means a lot if you can like this video and share it with your PM friends. Alright, I will see you next time. Bye. In spirit, you the data analyst.